Okay, so this is the complex methods in algebraic geometry, our bigger session. We have 3 talks. The third one is a Zoom talk. The first talk is by Henri Guenancia from the University in Bordeaux, and he's going to speak on the geometry of log Calabi-Yau manifolds.
Thank you, Christian. Thanks for the introduction and the invitation. It's my honor to be here today giving a lecture. So I will talk about a work in progress with Tristan Collins about Calabi-Yau manifolds, log Calabi-Yau manifolds to be precise. The beginning of the story is very classical and dates back at least to the 70s with the celebrated theorem of Yau that says that if you have a compact Kähler manifold with 0 first-term class, then in any Kähler cohomology class, you can find a Ricci flat galometric. So I think it's hard to sort of overestimate the importance of this result in complex geometry and the many applications that it had. I just want to briefly survey a couple of really beautiful applications of this theorem in the context of Calabi-Yau geometry. So this is the following sort of box. When I've gathered a couple of applications, it's going to serve as sort of thread across the talk. So first application is about the algorithm of such a compact Kähler manifold. And so you can see using Yau's theorem and Buckley principle that the algorithm is a holomorphic submersion, so it's subjective, smooth, and even locally trivial in the analytic topology. And you can actually prove that it's étale trivial, so trivial after finite base change, étale base change from the base. So this is one application. Another one is the polystability of tangent for any such manifold, and the reason is that if omega is Ricci flat, then the Hermitian metric induced on the tangent is Hermitian-Einstein, and by Kobayashi-Chain correspondence in the easy direction of it, that implies that the tangent is fully stable in a strong sense that I'm not going to get into today with respect to any possible polarization. Third application is something that I mentioned a couple minutes ago, is Buckley principle. So it's a bit maybe harder to formulate if you're not used to these objects. It's just saying that take your favorite holomorphic tensors. It can be a vector field, be a P form, it could be a symmetric differential, could be a tensor product of any of those. And then the theorem is that any such global section has to be parallel, so invariant interparallel transport with respect to the Kähler flat metric. And so the consequence of this is that the norm of that tensor is constant along the manifold, in particular, if such a tensor is not vanishing at a point, then it never vanishes. Okay, so this also has striking applications, including the Beauvais-Bouguereau decomposition theorem that I'm not going to get into today, but this is one of the key objects, and this will come back a bit later in the talk. Another application, which is somehow an intermediate step in the decomposition theorem, is the splitting of the universal cover of X has a flat factor across compact Calabi-Yau. Okay, so this is already a very strong splitting theorem. But, one of the take-home message is that at least, let's say X is projective to start with, then the universal cover of X is quasi-projective, which is an extremely situation that rarely happens, right? Conjecturally, it's essentially the only examples that show up when you have infinite pi1. So that's the sort of state-of-the-art, partial state-of-the-art about some application of the Yau's theorem. Okay, so a vague question that I wrote down here is to which extent this result can be generalized to a bigger class of manifolds, varieties, pairs, you name it. And this, again, it's a very vague question. I'm just going to take one route, possible route, but you could imagine formulating a similar question in many different contexts. So one possible context, and that was a very successful story, happened last decade or so, is for Kähler varieties with log terminal singularities in trivial first term class. So essentially the four properties that I wrote down in the previous slide still more or less hold. The first one is that there is on the regular locus of X some Ricci flat metric that's canonical once you fix a global Kähler class. And that was proved by Stugich and ZA about 10 years ago. So this is definitely the first step in the program, right? You have to find a metric that has nice curvature properties to then study further the geometry of X. Okay, one of the big drawbacks is that the metric is incomplete. You have a single locus unless X is smooth, and so there's a ton of stuff from differential geometry that you cannot do with it. So because of that, the next applications are not trivial applications of point one. The first one is that stability still holds with respect to any class. And that was observed for it's a different setting in the algebraic case for algebraic polarizations, like the Kähler and Pitton in 2011. And then this statement is was proved by me a few years later. Another application is the Albanese. That essentially the same property is true. So I put up a little star over there because technically you have to assume canonical singularities, but you can sort of find a cover that sort of reduces your situation to that case. So that's not I care too much about this, and that was due a long time ago to Kähler in the 80s, and this Kähler general situation, Mr. Crodon, Graf, myself, and Naumann, 2020. And again, the Bachner principle that also holds that says that, okay, if you have a holomorphic reflexive tensor, the more naive, what you think about is just a holomorphic tensor globally defined the regular locus, then it has to be parallel with respect to that singularity flat metric. Okay, so particularly if it vanishes at one point, it has to vanish at 4. Okay, so I'll stop here for the Kähler case, but that was one instance where sort of all the steps could be carried through very successfully to this more general class of singular varieties. So if you step out of Kähler and go sort of slightly further, to the boundary case of log canonical varieties, some of the arguments that tell you that in the Kähler case, the tangent is fully stable almost still work, but they give you semi-stability of the tangent. And so about a year ago, there's this really nice paper by Ricci, Ricci, and Calabi-Yau that was complemented by Niklas Müller shortly after, but they observed that statement, the earlier statements that I showed you just completely fail if you move away from Kähler singularities and allow LC singularities. So in particular, two major properties do not hold anymore. One is that the tangent, although semi-stable, will in general not be fully stable. And the Albanese map might have a non-trivial moduli, even birational. So a drastically different situation compared to the Kähler case. So one thing you could argue is that, okay, maybe this happens because there's no Kähler-Einstein metric somehow, and I do believe that there's no natural Kähler-Einstein metric on the regular locus of such a variety, and I don't know how to prove it, but you could maybe conceptually formulate this as an abstraction. I guess the point of the talk is to show you that no, it's more subtle than this, or somehow like just having a metric is not enough to derive the applications that you'd like to have. Okay, so let me move on to today's setting, which is slightly different. Instead of looking at singular varieties, I want to look at smooth ones, but where I add a divisor. And so that the complement is Calabi-Yau. So what I'm going to phrase this is I fix this compact element fold n-dimensional, and then I reduce the divisor with simple normal crossings such that the log canonical divisor is trivial. Okay, so in other words, you have a homomorphic n form with simple folds along D. That's never vanishing. And then you can ask sort of similar question. The first natural question is, does there exist a complete Calabi-Yau metric on the complement of D? Very much open in general. I think that the general answer should be no. But I'm not aware of an example at this stage. And then let's say you have one, which will happen in the rest of the talk, as you'll see. Then do we have a Bachner principle? Is it true that any holomorphic tensor, say logarithmic tensor, is it true that it has to be parallel with respect to? Yes. I guess it depends who you ask, but so there's one example in dimension 2, which is just P2, where you remove a conic and a line, and sort of we already know in that situation basically all the, let's say, all the known complete Calabi-Yau metrics on the complement. We know all of them that are itself alpha curvature, and we know that none of them live on that space. It doesn't exclude there's some like really wild metric that comes out of nowhere, but at least the intuition is that there should be some constraints on the pair X and D. Right, so let's assume you have one, like are holomorphic tensors parallel? If so, what's the holonomy group associated with that metric, so on. Third question is about the Albanese equivalent, so quasi-Albanese of the pair. Is it true that the fibers like don't vary in moduli? And then, okay, can you say something about the universal cover of the complement of D? And with the product structure, is it an open set and a compact Kähler manifold? Stuff like that you can ask. Okay, so today I'll be very modest and just study two very down-to-earth situations that are strikingly different in a way, even though they look a lot alike. So you fix the Fano manifold and you pick an anti-canonical divisor as a smooth or SNC with just two components that are mutually proportional. So for instance, Pn and any two divisors such that degree add up to n plus 1. Great. Okay, so right, I guess that's what I was trying to tell you is that we'll see in a second, a little more than a second, that in those examples, you do have a complete Calabi-Yau metric, and yet the answers to the questions 1, 2, 3, 4 are vastly different depending on whether you're in case 1 or case 2. I'll try to maybe give you at least one way to understand where this difference comes from, and what kind of stuff you can prove or disprove along the way. So for the next 20-ish minutes, I'm going to focus on case 1 and eventually move on to the second case. So, right, let me start with easy observations. You have a Fano manifold with a smooth anti-canonical divisor, and if you properly use a residue theorem, it's not difficult to see that any holomorphic one form with poles actually have to be holomorphic across D to access Fano. So you don't have any such form that's non-zero. Okay, so there's this first vanishing, the second vanishing, and the second statement that's actually stronger tells you that the complement of D is as finite fundamental. You can see this using our theorem. I'm not going to get into this, but this is sort of classic stuff. Okay, so consequence of that is at least two of the questions that I mentioned have an obvious answer. But since you don't have any logarithmic one form, the Albanese is just a point, so sure, it's locally trivial. And the complement of D has quasi-projective means to cover because it's just a finite cover of X minus D, right? Finite cover for quasi-projective manifold. Okay, so those two questions are out of the way, the trivial for some relatively simple reason. So what's next is, okay, do we have a Calabi-Yau metric on it? If so, it would be yes. What is the holonomy? Or is it true that holomorphic tensors are parallel? And what can we say about the stability, full stability of the logarithmic tangent bundle? So the metric first. So this was this is a construction that dates back to Chen and Yau and 89, maybe 90s. same setting, X smooth manifold, D anti-canonical, then there exists a complete Ricci flat geometric on the complement. That's very explicit, and it's as explicit as it gets. And that is in a way canonical. I don't want to explain why, because it would sort of take me a little bit of time to explain why this metric is canonical, but you can trust me, this is sort of the only reasonable metric to look at. And so let's see what we can do with it. So the first thing is, as a corollary of the construction, we know exactly the behavior of that metric near infinity. So if you think in terms of it's a complex analytic person, I don't know what that means, but in coordinates near D, this is roughly the shape of the metric. So transversely to the divisor, there's this like Poincaré-ish like growth, and normally to the divisor, the metric also grows, but very much more slowly. Okay? So that's the picture. I'm mentioning this because this is sort of relevant for the next slide. Once you have this model, it's not difficult to then understand the classic invariants that you attach to the complete Ricci flat metric. So one of them is you look at ball of its R in your geometry when R is very large, and you try to see, okay, what's the volume? So we know by theorem of Yau that the volume is always at least linear. And so here it's slightly faster. It's like 200 plus 1, which is subquadratic. Again, that will come back later in the talk. This is some crucial piece of information. And the second thing that you can check is, so if you look from very, very far away, you look at balls of very far, and you sort of rescale things to be size 1, what you see is just R. So sometimes the metric collapses all directions except for the direction normal, the real direction normal to D. So there's only one direction that survives at infinity. So it's a very slow growing metric. All right, so that's very classic things due to Tristan and Yau in the 90s. I'm going to be brief on this slide because that's not the main point of the talk, but from the asymptotics, what I'm claiming is it's not too hard to actually compute what's called the holonomic group of the metric. So I'm just going to give you a couple of sort of bullet points that explain to you where this is coming from. But you see immediately from the asymptotics that there cannot be any non-zero parallel forms of intermediate degree. You can also see this from a more algebraic way using a vanishing coming from Kähler vanishing. If you prefer, so that's the first piece of information. There cannot be any parallel P forms that are non-zero for P different from 0 and n. And the second thing is the fundamental group of X minus D is finite. So sort of, if you know a little bit about holonomy, there's a sort of, we know exactly the holonomic group in general is a complicated group. It might have infinitely many connected components that are related to pi1 being infinite, but here since pi1 is finite, the holonomic group is compact, and then we have the other sign specification that essentially tells, okay, we know who that is once you have information number 1. Okay, so I don't want to spend too much time on this, but this is telling you, sorry, that the holonomy is as large as it gets, as long as you're Kähler, Calabi-Yau, holonomy has to be Sun, and here it cannot be smaller than this. Okay, so what do we do with this? So the first result that I want to present in this setting of a smooth final manifold and a smooth anti-canonical divisor. So I fix this Yau complete Calabi-Yau metric. I denote by G the holonomic group of that metric. Yeah, sorry about the unpleasant notations, but essentially want to mimic homomorphic tensors. Homomorphic tensors are sections of Tx tensor P, omega X tensor Q, and here I want to work with logarithmic tensors. Okay, so I look at this vector bundle instead, and I look, so a V is the 5 other points. It's a vector space. And so our first result is that we have a Wagner principle in that setting, which means, so you go from the left hand side of the diagram here, you start from the holomorphic tensor, the holomorphic form if you want, or symmetric differential, and then you restrict it to the complement of D. That gives you a genuine tensor, holomorphic tensor. What I claim is that this tensor is parallel with respect to the Yau metric. Okay, so the arrow that goes in the other direction is sort of easy. It's a consequence of Riemann extension theorem, so I'm not going to explain much. But the statement of the theorem really is that any homomorphic tensors, you start from the left, and you restrict it to x minus d as parallel. And so if you know a little bit about holonomy, it means that you have a homomorphic tensor, it's completely determined by its data at a single point, and then to recreate it, you just parallel transport it along by parallel transport. Okay, so everything, all the geometry as far as tensors are involved is encoded in this group G and the representations of G. And so that's the sort of logarithmic analog of the classical Bachner principle. And the second statement is, so we do have the stability of the log tangent bundle and even stability. There's no, it's not a sum of different stable factors with the same slope. It's actually stable already, but only with respect to the polarization minus k. I don't know if it is stable with respect to any polarization. It's an interesting question, and you'll see, I'll try to give some ideas of the proof. You'll see why minus kx plays a role here. Minus kx is d, and so obviously this polarization is very much connected to the geometric section. Okay, so I would like to explain some elements of the proof of these two statements. I will not go through the full proof, but maybe try to give you some ideas, like what do we need to know to do on top of what's like the usual strategy in the compact case. So that's the next slide. So how does it work? So you start, again, what I want to prove is I have a homomorphic section of, let's say, logarithmic tangent bundle, logarithmic tangent bundle, and I want to show that it is parallel with respect to the tangent, which means that its covariant derivative vanishes identically on x minus d. So I take such a section, I look at its norm, and Bachner formula tells me, because the metric is Ricci flat, this celebrated identity of the Laplacian of the norm of sigma squared is equal to the norm of the covariant derivative of sigma squared. Okay. Then you do a little bit of rearranging stuff, very classical. Instead of looking at the norm of sigma, it's more convenient to look at the log of the norms. That's the function that I call f. And with Bachner identity implies it's essentially that discussion Schwartz that f is subharmonic with respect to tangent. And because sigma is a homomorphic section of the log tangent bundle, some tensor bundle, and you know exactly the shape of the metric at infinity, it's not hard to see that the growth of f as a function is in the log of the radius to a fixed point. Okay, so it has very slow growth. This is exactly why we want to take the log of the norm, rather than the norm that might blow up very, very fast. Okay, and then you sort of want to say, well, I have a subharmonic function. If x were compact, then you integrate this. The integral of Laplacian is 0. So the Laplacian, that would tell you that f is sorry, so you multiply by f, integration by parts tells you immediately that f is constant, and then you're done. All right, here x is not compact, x minus d is not compact. So you have to use some cutoff function. So I have this ball of radius r, very, very large, and I take a function that's 1 on the ball of half the size and 0 outside of that ball. Okay, so standard Riemann geometry tells you the Laplacian of such a cutoff function decays quadratically with a radius. Okay, so then you integrate. Instead of integrating the inequality Laplace f is non-negative, you multiply that by the cutoff, so that then essentially you can apply Stokes' theorem, right? So you have that 0 is less than the integral of chi Laplace, and by Stokes, this is f times Laplacian of the cutoff function, and by what I've explained, you have 3 terms. You have the contribution of the Laplace of the cutoff, that's the last term, 1 over R2. You have log R, it's the contribution from f, and then you integrate over the ball of radius R, as I explained. This is R to a power that's slightly smaller than 2. Okay, so this actually goes to 0. And this is where it's crucial that the volume growth is subquadratic strictly. That implies that the Laplace of f is 0, and then you're very close to home. Yau theorem tells you that since f grows sublinearly, it can only happen if f is constant. But if f is constant, then the norm of sigma itself is constant. And then you plug that back, in the Bachner identity tells you the Laplace of norm of sigma squared is 0, because it's Laplacian in the constant. So that's the covariant, the normal covariant derivative of sigma. So that's how you get by. So that's the proof of 1. Okay. So proof of 2 is more involved, not as sort of pleasant to explain. The general crowd, and it certainly has overlaps with a paper by Chen Chang, Higgs bundles and non-complete manifolds, and Ricci flat metrics. So I'm going to try to just highlight a couple of important steps and see, right? This session is about analytic methods in algebraic geometry, so I want to show you where analysis is involved in the proof of this. So you want to show that the logarithmic tangent bundle is stable. You already know that it's semi-stable. So all you have to show is to exclude that there cannot be a subbundle or subsheaf that has 0 slope against minus the x or against d. Yeah, so that's, we want to show that it's not possible to have this with f being a proper subsheaf. Okay, so it's an argument by contradiction. Suppose I have one, or simplified notation that sets a subsheaf of rank 1. The first step is to look at what happens d near the divisor d. And near d, you can actually prove that the restriction of that logarithmic tangent sits in an exact sequence between the tangent of d and OD, and that exact sequence is split. That tells you that that vector bundle over n plus 1 is a direct sum of the tangent bundle of the Calabi-Yau of d, which is stable by as a consequence of the Yau theorem, and OD, which is also certainly stable of rank 0. So that's fully stable. And so from here, it's not difficult to maybe you have to modify f, but then that tells you, okay, I can assume basically that near d, my destabilizing subsheaf f is one of the two factors, because in particular it's locally free. There's a little bit of work to achieve this, but this is not very difficult. And then, okay, you want to compute slopes using special metrics. That's a very classical thing to do. That's exactly what happens in Kobayashi chain correspondence. You use metrics with special curvature to derive information about slope of subsheets. Okay, the difficulty here is that you work on open manifold with metrics that have infinite volumes. So computing slopes with metrics with infinite volumes, I'm sure you can convince yourself that that can't be easy. Right? A summary normalization argument has to happen, or something has to be done, right? So this is sort of a bit technical, so I'll go a bit fast. I just want to highlight a few important ideas without getting into the more gnarly stuff. But the point, again, is very classical. So you have your Calabi-Yau metric on x minus d. So this is a smooth metric. You can see it as a smooth metric on the tangent away from d. And you use this to measure slopes of your subsheaf f. Yeah, so there's a famous formula due to Griffith that tells you that there's an inequality, or better there's an inequality. And here, I'm skipping the details, but the point is, you essentially want to compute an intersection number that looks like C1 of f against dn minus 1. So you do this at the level of forms. You present C1 of f by the curvature of f with that single metric. You wedge it with the Chen-Yau metric with the power minus 1. And then the Griffith's formula tells you that this has a sign pointwise. And this is very explicit. The obstruction to not being zero somehow lies in the fact that F admits a holomorphic complement or not near the point somehow. That's the second fundamental form. Okay, not very important at this point. And the name of the game is to show that the integral, let me show you again, the integral on the left-hand side, if I can show you that the integral of the left-hand side is non-positive, is non-negative, zero, it's zero, then that will tell you that the form on the right-hand side is pointwise zero, and that will tell you that F is holomorphically complemented by its orthogonal with respect to the geometric, and that will contradict the holonomic computation that I showed you a couple slides ago. Okay, so essentially, this proof will mimics the polystability statement, but here, because we already know the holonomic, polystability will immediately imply stability somehow. So, right, you have to show something like this. And as I said, the first obvious comment that you should have is, well, this is a divergent integral. You're integrating some form, the curvature of F, that is very quite wild infinity first. And second, you wedge this with a metric whose volume is infinite. Okay, so this integral a priori has no reason to make sense. So I have to justify that, what I mean by this integral is zero. And this is the meaning is that, okay, I look at the cutoff function, I integrate the cutoff function against this volume form, and that quantity goes to zero as the cutoff function exhausts more and more of the manifold. Okay, so I'm not going to show you why, but I'll just tell you some important ingredients. So obviously, we have to use at some point that the slope of F vanishes. If not, we would have a divergent integral. We have to use step one in a sort of subtle way, but this is crucial from an analytic perspective. And then we really use that we know the teniometric very, very well at infinity, so that the integral that we're computing sort of can be reduced to explicit integrals of explicit volume forms. And these can be computed, and error terms can be shown on the model to be zero. So there's quite a fair amount of computations involved in there that I don't mean to explain. I just wanted to give you some like important ideas. And as I said, so given step two, once you show that the blue integral is zero, then the integral that was on the right-hand side of the formula has to be zero as well. And that tells you that F, so the possible stabilizing subsheet, is holomorphically complemented by its orthogonal complement with respect to the teniometric. That tells you that the holonomy fixes the proper subspace, and SUN acts in an irreducible way on Cn, so that cannot be the case. Well, that's a contradiction with the holonomy notation that I made earlier. That's the proof. Okay, so that's for sort of the case, the easy case of the easier case of a final manifold and smooth anti-canonical divisor. Let me move on to the second case where things will change drastically. So that's the setup, as I hinted at already. So you have a final manifold dimension of at least 3. And you pick two divisors, D1, D2, smooth, intersected transversely, such that the log envelope is 3. And there's this restriction that you want these D1, D2 to be proportional. So for instance, they have this Bn and then they're in business automatically. Okay, so easy observations is you have those two divisors that let's say D1 is D2, and you can consider sections of a D1, section of a D2 that vanish along D1, vanish along D2. You do the quotient of that. It's a homomorphic function that is projected onto C star. Okay, so you do have a map from X minus D to C star, and it's not hard to see that this is a quadrature of the pair, which means that all the logarithmic 1 forms of the pair XD actually come from differential of the log holomorphic function A. Okay, so log A is not defined, but the differential of that is. Okay, that's the That's the generator of the space H0 of omega x1 log d. Okay, the third observation is that topologically the situation is very different from earlier. Here, one of x minus d is infinite, essentially z up to a finite factor. And what happens is you have those two components, and there's one loop, which is you wrap around d once, and you wrap around d1 once, and then you wrap around d2 in the other direction, and then you loop back up to your point. And that loop it generates at least the z part of the pi one. So geometrically, that's the generator of the pi one of the complement. Okay, so that's all like relatively elementary observations. And all this, let me consider a specific case where x is Pn and d1, d2 have the same degree, so that means that n has to be odd. And I want n to be at least 9. I'll explain that in a second why. And then you have those two statements that the quasi-Albanese, which is the map to C star that I wrote earlier, the fibers of that, two virginal fibers, which I said two virginal fibers of that, my mouth actually little. So let me just move to point 2 and then I'll say a bit more about it. And also in that example, basically for the same reason, the logarithmic tangent formula is not fully stable with respect to any, well, in this case, it's only one Kähler class, but scaling, so it's not fully stable. Right? I wrote this as a proposition. So first remark, I want to say this is a map. Different example and mirrors the earlier work that I talked about. That it's going to be, let's see, techniques like Ferri and Rula. Sort of also shares similar flavors. The point is that, so I wrote this as a proposition because in a way it's more of an observation. Once you have proof of one relies on very, very deep result by Stefan Schreider and Evgeny Shinda that guarantee that in that range of numbers that I picked, so hypersurfaces of that degree, virginal ones, are never irrational to each other. Okay, and that's a consequence of the fact that they're not stably irrational. Okay, so that's some very deep facts, but once you have those facts, then essentially it's just a direct application of their theorem. And the fact to go from 1 to 2 is the same strategy as in the appendix written by Niklas Müller. Okay, the point is there are probably plenty of such examples, right? If you pick well chosen like pair, what can be a pair? It's likely that these two things will also be true. So somehow the failure of the polystability of the log tangent and the failure of the culturality of Albanese should, I suspect, be generic. Okay, in the remaining time that I have, I'd like to move to point number 4, if you remember. You probably don't, so let me repeat. Point number 4, if you remember, compact element pool. You take its universal cover, then it's Cn cross something compact. In particular, it's an open set. It's a Ricci open set in a compact Kähler manifold. You can ask the same question here. That's good testing ground. You have x minus d. This has infinite pi 1. Okay, so there's something to test on. You look at the table universal cover of that, and you can ask the question: was that projective? Is that Ricci open set in some compact analytic space? So that's the direction that I want to take you to now in the remaining 10 minutes. Same setting, Xfano, 2 divisors. If you want, you can just take Pn and 2 divisors of the same degree n plus 1 over 2. Okay, then the first step, we need, it's good to know that there is some Ricci flat metric somewhere, and this was constructed quite recently by my collaborator, Tristan Collins and Young Lee. So it was published a year ago, but I think this dates back a few more years. And they showed sort of like building on the Tanyel theorem that even in the case of two divisors, as long as the dimension is at least 3, so the dimension is larger than the number of divisors, this is really what the important point is. Then you can construct a completely flat metric on the complement of the two divisors, and somehow that matrix away from the intersection looks like a Tanyel-like metric, and near the intersection has a complete different behavior, and this is where all the geometry concentrates somehow. So you can think in terms of volume, take a ball where is R, 99% of the volume of the ball will go in the, you think Euclidean and locally in the neighborhood of the intersection, just somehow counterintuitive. That's what happens. So it has very different geometry compared to the Tanyel geometry, right? So I guess a consequence of the asymptotics of that metric is the volume growth is, you can think of it as double the volume growth of the Tanyel line. So it's super quadratic in particular. And the tangent cone is 1 dimension higher. So remember the tangent cone infinity in the Tanyel case was just a line coming from the normal direction divisor. Here you have two divisors somehow, so you have two normal directions where you have the normal bundle of the two. It's a vector rank 2 vector bundle, and those two directions contribute each one for the asymptotic tangent cone. And that also explains why the volume sort of almost doubles volume growth. Okay, the exact expressions of all these don't matter, the numerics don't matter, but keep in mind that the volume growth is super quadratic, so that the argument that I explained to you earlier doesn't apply. And for a reason, because we have this holomorphic 1 form with log poles, which is differential of the log of the Algebraic, right? So the generator of the space of holomorphic 1 forms with log poles on D, that one you can check immediately on the shape of the Kähler metric is not parallel with respect to the Tanyel metric. Okay, so in the first case, the fact that the volume was subquadratic allowed me, with some technique and computation, to show that holomorphic tensors were parallel. And what I'm claiming is this is not accidental, but this property was used, because in this example that is very similar with the volume growth is slightly bigger than 2, then you do have tensors that are not parallel. Okay, so that's already a very different picture. And so what we prove about this metric is sort of like threefold. We also compute the logarithmic for this metric. It's a bit more subtle than for the case of 1 divisor. If I1 is infinite, so if you have to come up with an argument to measure the difference between restricted logarithmic and full logarithmic, but that can be done. And we show that it's the maximal one. In particular, it's not hyper-Kähler, which was not maybe clear at the beginning. And then we can explicitly understand the geometry, the Riemannian geometry at infinity. Again, the numerics don't matter. You see the volume growth sort of increased by 1 unit. And that's reflected by the fact that on x minus d, you have those two divisors. And as I said, there's this loop that wraps around both divisors. And the universal cover unwinds to somehow you can think of this as a family of circles, right? Of circles that are wrapped around D. Take the universal cover, this becomes a family of lines. And this family of lines, that's contribute a further direction that's not collapsed by the metric. Okay, so instead of having a two-dimensional tangent going to infinity, then there's this additional direction coming from the circle that's being unwrapped in the universal cover that contributes to the Riemannian geometry at infinity of that metric. Okay, so it's an interesting feature. And the last point is that you can find several different types, the ones that I introduced, of examples of XD as before, where the universal cover is not compactifiable. You cannot realize this as a Zariski-Open set in a compact complex space. This would think. So it's a Stein manifold. It's very nice. It has a vibration to C that's very complicated. And right, so it's not, doesn't come from the complement of a divisor in some compact space. Okay, so somehow it's in a way a different type of complete Calabi-Yau metric. Examples of that flavor were constructed, I think, in the 90s by Henderson, Lebrun, and Kornheimer, dimension 4. Okay, I'm not sure if there have been many examples, such examples that arose after that, but that's sort of provides infinite families of such examples. Okay, so I'm essentially at the end of my talk. I've just one more slide that's a table that shows you so the complexity of the situation. Right as I started talking about Yau's theorem, compact Kähler manifolds with zero friction class, where you had all these properties. You have Calabi-Yau metric, Calvinese is locally trivial, right tangent is fully stable, the Barker principle that holds, and that it also covers whether projective or a Zariski open set in a compact space. And basically all these properties carry through to the KLT case, with maybe one that we don't quite know yet, that's very strongly conjectured. We don't follow some compatibility conjecture is that the universal cover on the regular parts of the KLT space with 0.0 should be either quasi projective in the right case, Zariski open set in a compact Kähler space. That we don't know, but we strongly suspect it. And as soon as you move to the LC case, essentially everything collapses. So it's just this strong evidence that there shouldn't be a Calabi-Yau metric on the regular part, or if there is one, has nothing to do with any of the metrics that we know. You don't have locally trivial Albanese, you don't have full stability of tangent, and Faulkner principle doesn't make sense because it's pretty metric. The universal cover of the regular part of X, I'd be very surprised if that were to be always projected, but I'm not sure that there are cameras on the stage. And then sort of move another direction of logarithmic pairs. I just consider pairs with a silo and D is smooth, or with two components, more, that's at least two. And the first line is yes, wonderful. Second line is yes, we have metric, but essentially all the rest, like all parts, we collapse it. And that was somehow a surprising discovery to us, but despite the existence of that metric, essentially all the natural properties that you could expect are just plain wrong. Okay, so my time is up. I'll end with this, and thank you for your attention.
Okay, thanks. Other questions? Yes.
If you can have a word as for how you show that the universal color to have.
Yes, so there are two examples, so with different flavors. One is if you take Pn, one hyperplane, and 1 degree n hypersurface, and then this was known that the homotopy type of X is it's a wedge product of S1 with a wedge product of Sns. When you take the universal cover of X, then you get something with infinitely many Sns that contribute to infinite homology. So not only it's not compactifiable, but it doesn't even have the topology of, that's essentially how you contradict the statement. It doesn't have the topology of the complement of a Zariski set in let's say projective manifold. The second example is the one that I mentioned with the two same degree hypersurfaces in Pn. This one, that's a bit more complex and in a way a bit more interesting. We can have a similar phenomenon where we have infinite topology. Point is X minus ds vibration, which is a Lefschetz pencil with at least one single fiber. That vibration, when you sort of like lift it to the universal cover, gives you a vibration over C with infinitely many single fibers, and somehow you can link all these single fibers that are translates under the Galois group by vanishing cycles, sorry, and those vanishing cycles are independent in homology, so that creates independent homology.
So if we would know actually the existence of a complete metric in the case of more devices.
Yeah.
Just the two, because you know that the metric exists, right?
It's just conjecture in that case. The effect is fine. It's almost no. Yes.
Yeah. So in that case, your theorem would go true.
So in that case, it turns out that most
Can
of
you repeat the question?
right. Sorry. So the question was, instead of two divisors, I have the number of divisors with strictly less than n, and let's assume there is a Calabi-Yau matrix on the complement. How much of the story carries through? And the answer is a lot of it, because at least the holonomic computation will be the same, because all it cares about is the behavior generically in dimension 1, and that would be the same as the Tanyao case. So for that property, having so failure of Bachner will also be true. Holonomy will still be SUN. Full stability, and we can probably cook up similarly almost to these ones. But I didn't think those. But because
Yeah, that would be
okay,
sure. Then you also use the fact, because I guess the problem, like you have two divisors, the problem is that they have the behavior at the intersection point.
Yeah.
Right. And then in that case, so all these they do know this behavior, right?
yeah, it's completely explicit.
Okay.
Yeah, that's I mean I wrote a very
It's just because I'm here myself, we understand each other.
I will repeat the question. I will repeat it.
The asymptotic behavior at the intersection point is the more difficult point. You ask, the question was, what is the asymptotic behavior then?
So there's a fair amount of work in the case of several divisors, still all proportional. If they're not proportional, so now the problem is almost more interesting. No, less interesting, because then the power of the complement is tiny. But let's say they're proportional, and you have 3 divisors in something dimension 4. Then it's expected that the way somehow the Legendre equation associated with that almost being solved. What we don't know is regularity, and whether we can move all these pieces together. So we sort of like conjecture of that have nothing to do with this, but like Collins, like strict on for long, Yau was involved in that paper. So there's very strong evidence that we know what the metric should exist and how it should look like. It's much more complicated. And then the geometry does also concentrate in the more singular stride, which is the Calabi-Yau. And then it's expected that the volume growth will keep getting bigger and bigger. So definitely all these arguments fall apart.
So, is there anything that can be said about the non-collapsing case? It seems that for the Wagner principle, it really needs very strong collapsing, but without holonomic groups.
So there's the class of natural Calabi-Yau matrix when instead of Kx plus D is 0, they have Kx plus 2D is 0, where then the associated Tanyao metric is asymptotically conical with maximum volume growth. And so then the volume growth is even bigger, and it's solely there's solely no we know the holonomy for these metrics, and we know that Bachner principle. It wouldn't be clear to formulate properly Bachner principle here. The fact that the coefficients in front of dr1 tell you that the good vector problem is to look at a logarithmic tangent or logarithmic cotangent. If you were to look at geometries when stuff Kx plus D is 0, you have Kx plus 2D is 0, or like 10D, you'd have to look at orbifold like tangent pairs or something like this. And then I suspect that there's still no Bachner principle for those tensors, but I haven't really looked at it.
There was I'll give you the microphone. I just worried about him.
So I'm just wondering, so in your example, this P2 with 2 hypersurfaces?
Yeah.
the logarithmic tangent bundle is not polystable, but did you at some point mention it's semi-stable or?
So it's always semi-stable. If you have any log canonical pair, then Tx of minus log D is always semi-stable. That's true, yeah.
Yeah, so then my question is that, so even though it's not polystable in, that example, does
Yeah.
it become polystable after some finite pullback? Like some finite couple, a time, away from the divisor.
No, so, no, I don't think so, because if you take a finite pullback, let's say, italic, right? Then you'll still have the same algorithm map. Basically, you take the fiber product of that, right? And essentially, you're not. Like, because any cover has to come from a cover from the algorithm morphism. So somehow you're not going to change the quasi-algorithm. If you do this, which means that you'll still have the same abstraction of having a map to something with a trivial log tangent that doesn't split, that cannot have a splitting. So I think that for the same reason, I think the same argument applies to finite covers as well.
I should. If we fix the fundamental and we degenerate the smooth, any canonical smooth divisor into like two components.
Yeah.
What can we say about like family of tail meshing? Do we expect it will converge to the Collins state meshing or not?
That's a very good question. So I would expect it. I don't have more insight than this, but I at least think about it for 3.5 seconds. I don't see a bigger obstruction. Yeah.
As you mentioned, like the geometry is quite different. Or
So geometry is quite different. So probably what will happen is you might have smooth convergence like away from the divisor, right? Then like the general matrix as the adjoint to something singular will become more and more complicated. So the question is whether you can find a good model that's sort of uniform along the degeneracy of the divisor. It's probably a difficult question, but I suspect that might be done. I don't have insight on that.
okay, thank you.
I have one. How unique are these non-complete Calabi-Yau matrices?
So that's a touchy subject. So usually in Riemannian like geometry, those unique, all the uniqueness statements, like you fix the geometry at infinity with some convergence, then there's a unique such metric. Let's say you fix the column on J class, and then there's up to scaling exists a unique such representative, but that means imposing sort of the model infinity, right? So among all the metrics that have roughly the same asymptotics, then there's only one that's Ricci basically. So that's usually where the uniqueness statements are formulated. In the Tianyao case, the simplest case, there's, I think, a more satisfying way to answer your question, but again, that depends who you ask. That metric is so right, you have kx plus d, which is 0, then kx plus 1 minus epsilon d. This is negative, so you have the log family pair. It turns out that these log family pairs, they have a unique Einstein metric with positive curvature and frequency value 1d. They're unique, and they converge as epsilon goes to 0 to that metric. That's telling you somehow this is a canonical map.
Yeah, they got something similar for the Collins leap.
It's not known. Some people have tried.
Okay, all right. Then. So let's thank Henri again very much for his talk.
Yes.
Okay, the next talk is at 2:50, so 20 minutes. The beginning is not so good for the questions.
It was like, it was almost on purpose. There was one question here and one there.
Yeah.
Ping pong, right?
Okay, so I stop the recording.
So I want to